Hey guys, so problems 1 and 2 are very similar. I will deal with them separately just for emphasis, but you should know that you should be able to see the fact that they're very similar. All the changes is this distributed load, the direction of this distributed load, and that will have minor effects on your reactions. It'll have more noticeable effects on your shear and moment diagrams, and it'll have very little effect on your displacement diagram. So let's get started. You have some frame that looks something like this, and for some reason I keep mixing up which one is the pin and which one is the roller, but I believe I have this correct this time. So in the first case we have just a triangular load. So in the last video, in the 0 video or the introduction video, I already showed how to work with the triangular load, but I'll show you some tips briefly here. Because this is the first video, let's get the reactions. Make sure we know how to do the reactions. If we do sum of forces in the x, we get Cx plus WL on 2. Write this, the base, times the length, divided by 2. That's the total force due to the triangular load. Equals 0. Cx equals negative WL on 2. Now we have, let's do moment about point C in order to get MA, or just in order to get AY. So if we do plus MC negative AY times 2L plus, this is force times the distance, AY times 2L. Sorry, this is 2L, this is L. This is the total force to the distributed load, as we had before. And we're going to multiply this by the distance between here. This is L on 3. We do that, and we get AY equals WL on 12. And from sum of forces in the y direction, we know that CY is then negative WL on 12. So those are our reactions. I skipped a couple steps for you guys, but it'll be good for you to fill in the blanks. Once we have our reactions, we can start with we can make a cut. And we can go something like this. Note that in this problem we actually do have the axial load. It's actually fairly rare. But the real question is, how do we deal, sorry, this is V of x. The height of the distributed load at some point on here is W of x. We want to find out an equation for the height of that triangle, like we did in the last video. If you have trouble working with triangles, please see the last video. But I'll outline this briefly here. So W of x is going to be equal to W on L times x. It's very important that you have a function for W of x. Your equations will be all wrong if you do not have a function for W of x, because W is not constant, or your distributed load is changing with height. If we do sum of forces in the y direction, we get that A of x plus WL on 12 equals 0. A of x equals negative WL on 12. If we do sum of forces in the x direction, we get V of x plus W of x, which is the height of the distributed load, times x divided by 2, which is the length times 1/2, which turns this distributed load into an area. So we get the total distributed load at this point equals 0. So V of x equals negative Wx on L times x on 2 equals negative Wx squared on 2L. Our V of x equals negative Wx squared on 2L. If we do moments now, it's hard to find a good place to put the camera up. My desk is very small here. M cut M of x plus W of x times Again, this is the total load to the distributed load, and this is the distance that the force acts from the distributed load. And again, we have m of x equals negative x cubed on 6L. Note that my w of x is a function of x, my v of x is a function of x squared, and my x cubed, or my moment, is a function of x cubed. And you should see a similar progression of your powers. The highest power should always be 1 greater than the power from the previous level. So I have all these. Now, I can just... That is for the vertical member. We also, I'm trying to find my sheet. We also need a cut for the horizontal member. So we made a cut here. We need a cut for the horizontal member. That is actually fairly straightforward, I think. We have x. The positive moment is this way, and the positive shear is this way. My c of x is negative WL on 12. My c of y is negative WL on 12. My sum of forces in the fx direction will be a of x minus WL on 12 equals 0. A of x equals WL on 12, and I think I had the signs reversed. What did I do here? I have the signs reversed here. Sorry, let me start this again. A of x, negative a on x, plus cx equals 0. Negative a on x minus WL on 12 equals 0. A on x equals negative WL on 12. So I should have kept track of my signs better. My Fy, V of x plus Cy equals 0. V of x equals negative Cy equals negative WL on 12. So my V of x equals positive WL on 12. That should be apparent here. There's only a single reaction here. There's no forces in the middle. My shear should be equal to that reaction. Okay, now let's work with the moments. That's my positive value here. M of x minus cyx equals 0. My m of x term should equal cyx. M of x equals negative WL on 12 times x. That is my moment equation. Now we need to check something here. We should get something interesting. This is the moment equation along the top. Do you guys, the distance between C and B is 2L. When I plug in m of 2L here, I get equals negative WL on 12 times 2L equals negative WL squared on 6. I also have, so this is moment at B. I also have an equation going from A to B. Right? So my m of x from A to B is equal to negative wx cubed on 6L. When I plug in x equals L, right, because AB is only L, length L, it is not 2L, I get L squared on 6. And that, these two should match. And these two should match both in magnitude and in sign. So they should actually be equal to each other. They are equal to each other in this case, so that is good. Finally, we have the question on how do you draw your diagrams for this problem. And it's always best if you draw them directly on the frame. So what do we mean by that? We say that often, but what do we mean by that? We have some pin here, some roller here. I'm going to make the positive on the outside, the negative on the inside. what is my axial force? Well, my axial force in the vertical member and the horizontal member is negative WL on 12. So I'm going to draw a negative WL on 12 value. Sorry, did I mess this up again? How did I? Oh no, what did I mess up here? I do not want to make the first 10 minutes of this video again. I'm sorry, this force here is WL on 2, not on 12. Negative WL on 2. This axial force should be negative WL on 2. Okay, so I should get some force negative WL on 2. And let me change colors here. This will be negative. What about the vertical member? For the vertical member, I should get negative WL on 12. Right, this is for the vertical member. I should get negative WL on 12. So this is negative sign again, just less negative. And we get a graph that looks like that, and it's always good for you to label your diagram. This is negative WL on 2. Okay, so that is your axial force diagram. Now let's look at shear. So for your shear, we start off at 0 shear here. Normally you start off at non-zero shear because you have a reaction, but in this case there's only a roller, and that roller is only causing a axial force. So in the vertical member, I have negative WX squared on 2L. That is the equation of my line. So it's just, it starts off at 0 and it's parabolic. And it is negative. And again, I'll make my negative on the inside. And I'm going to go with something like this. Negative L on 2. That is my shear. My shear in the other direction is just going to be linear, I believe. No, it's going to be constant, sorry. It's going to be constant, and it's going to be positive WL on 2. It's going to be constant, it's going to be positive WL on 2. Okay, so that's good. We have our positive 1. Now what about the moment diagrams? The moment diagram, I'm going to draw the positive on the inside. Moment is going to start off at 0 again. It's going to start off negative, and it's going to slowly increase. Sorry, it's going to increase more and more quickly. Decrease more and more quickly. So my negative is on the outside again. And this is supposed to be cubic. So WL squared on 6. It's a cubic shape, but the value is squared. And up here we get some negative. And again, both of these values are the same. Finally, let's draw the deflected shape. Basically, what's going to happen is this roller is going to move inwards. If this moves inwards, this has to move downwards. So we should get, and this has to stay at a right angle. So we're going to get something that looks like, this is going to be concave downwards, and we're going to get something over here. Alright, sorry I'm running out of time here because I can't make videos longer than 15 minutes, but I guess we'll go on to number 2. This is everything you need for problem 1.